Also, second talk is by Andrew Lampinen from DeepMind about symbolic behavior in AI.
Awesome. Thank you all for having me. This should be an interesting talk. So to set the scene for this talk, I want to take you back to 2020. It was the dark ages of AI. We were all sitting in poorly generated castles like this one. And me and some of my colleagues were talking about symbols for a while, and we came up with this paper, Symbolic Behavior in Artificial Intelligence, that we put out, I guess probably more like the beginning of 2021. And so this paper was written in a particular context. The context in AI has changed, but Antonio and David kindly invited me to come talk to you about it. So I'm excited to talk to you about it. At the end, I'm going to start by telling you about the paper as I saw it then. Then I'm going to try to bring it back to something about whales at the end. And then I hope in the question section, you all can tell me how little I know about whales, because I know almost nothing about whales. Maybe we can brainstorm about some better connections. OK, so the question of this paper was, what is a symbol, and how should we think about that in AI? And I just want to give you all a second to think about that. So what is a symbol to you? Each of these things could be thought of as symbolic in some sense. Canadian flag, some code, an erased drawing by someone. But these things aren't symbols in isolation, right? They're symbols to someone who's interpreting them. A frog looking at the Canadian flag might think it's a leaf in some circumstances, but probably isn't going to see it as representing Canada, right? And so there's a long history in AI of thinking about symbols in particular ways, and a lot of this goes back to Newell and Simon, who originally defined symbols as a set of interrelated physical patterns that could designate any expression whatsoever. But this question of whom they're designating something to is very important. And this already came up in fairly old critiques of how people thought about symbols, including this one from Turetsky and Pomerleau, who discussing the discussion of symbols in the context of this early self-driving vehicle, said that if you call patterns a symbol whenever they can designate something, that basically means that nothing isn't a symbol as long as some system is using it for some sort of communication. Even the electrical signals in a modern doorbell are a symbol by this definition. And that's not really an interesting definition of a symbol. So in this paper, what we did is we took some inspiration from this fairly old philosopher, semioticist, Charles Sanders Peirce, who defined a symbol as a representation whose meaning is established by a convention. Some people or some person agree, or some entity agree upon a link between some arbitrary substrate, as we heard earlier, and its meaning. And this is to distinguish symbols from other kinds of ways meaning can be denoted, such as icons that get their meaning just by the fact that they kind of look like the thing they're referring to, and indices that get their meaning by some sort of correlation pattern of how those things are associated, like a thermometer or a speedometer. OK, so why am I telling you this? Why does the definition of symbols even matter? Well, again, this paper was written in a particular context, and the context in which we wrote this paper was that there was quite a bit of hand-wringing in the literature about the need for more symbolic inductive biases for our architectures to get good generalization, to get systems that were really intelligent. And these are a few examples of these kinds of papers. But what we felt was that maybe even this focus on architecture itself was misleading. And maybe it comes down partly to the definition of symbols that we use. And in particular, what we tried to do in this paper is to argue that we should focus on behavior. So what we care about as a consequence of being symbol users is the behaviors that we demonstrate as symbol users. And we thought that this definition of symbols as being conventional, having meaning by convention, affords different types of behaviors than the ones that people typically think about in computer science as being symbolic. And we suggested that these behaviors are actually more aligned with the kind of human capabilities that we're most interested in, such as our ability to flexibly communicate across many different situations, or even our ability to use symbols in more typically thought of as abstract situations like advanced mathematics. All right, so what are the behaviors that demonstrate use of conventional symbols? So in this paper, we outlined 6 different behaviors that we thought of as demonstrating this kind of symbolic behavior. Why 6? Well, no particular reason. We had 7 originally, and then we decided one of them was too similar to the others, so we got rid of it. So this is just sort of a loose collection of things, and I'm going to tell you about how they fit together over the next few slides. So the first behavior that we thought was absolutely critical for demonstrating some sort of understanding of symbols is being receptive to them. So that is the ability to understand an existing convention of meaning and to receive a new one. And of course, Many systems do this. Children do this all the time when they learn the meanings of words from their parents. And this is also something that most AI systems do in some sense. So all supervised learning consists of some sort of imparting of static conventions onto our models. But there's also some systems that have more ability to sort of rapidly adopt new meanings, such as language models or various meta-learning or RL agents. And of course, many animals exhibit this kind of receptiveness too. So this is just, we start with this one in part to illustrate the fact that being receptive to symbols or any of the other criteria that we're going to outline alone is not sufficient for making a system, for saying that a system exhibits the full range of symbolic behavior. Now, the next criterion, which we were a little more interested in, was the fact that symbolic behavior is constructive. And what we mean by this is the ability to create new conventions, to impose meaning on new arbitrary substrates. And this is something, for example, like defining a new mathematical construct because it allows you to prove a theorem more easily. And this is something that we think is really fundamental to flexible use of symbols. And it's something that's less common in AI. Oh yes, and a point I want to highlight here is that we do think these conventions could be something that's that's generated within oneself. Like if you're proving a new theorem, you might come up with a new definition yourself. It doesn't have to be defined in convention with somebody else, but it's just like you are in some sense deciding on a meaning. Whoops. And this is something that comes up much less often in AI. You can sometimes see language models do certain things that look a little bit like this, but they generally don't do so in such a purposive way as humans do. Like they don't define a new concept because it's something that would be useful for achieving some goal. Maybe in emergent communication, you get a little bit of this, but not too much. So the next criteria we had was that symbolic behavior should be embedded. And what we mean by that is that symbols should be part of a larger system of knowledge that they fit within. So first of all, we took a sort of, let's see, I may get my time periods wrong, early Wittgensteinian perspective that meaning is determined in part through its interactions. So symbol meaning is determined by their relationships to other symbols in part. And this is part of the reason that we think that a theoretical development in a field can fundamentally change the way we think about a lot of the other concepts in that field, right? Because the meaning isn't determined in isolation, it's determined through how those meanings interact with everything else. A second kind of embeddedness, of course, that's very important to humans and presumably to whales is the fact that we rely on sort of embodied understanding. Well, maybe I shouldn't say presumably to whales. I don't know about that. But humans have been thought to rely on embodied understanding, such as gestures, to help us understand abstract concepts from math or science. There's been some pretty interesting studies on this from people like Susan Goldman-Meadow. And in AI, well, I think one of the nice things about deep learning, at least as we argued in this paper, is that these systems are strongly biased towards embedded understanding. But what that means is that you need to get the embedding right in order to get them to achieve the kind of understanding you want. And in particular, it's possible that language models might need some sort of situated multimodal experience in order to understand some of what there is to be learned from language. So just to do a little bit of a deep dive on that, I'm going to tell you about a more empirical paper we did a few years before, where we tried to study how embodiment could affect language learning. And the way we set this up is we did sort of a classic compositional generalization test, where we trained a system to recognize objects in colors by learning from some pairings of objects in colors. Then we tested it on its ability to recognize held out sets. And the way this test was set up was that the system would see two objects, it would get an instruction, and it would have to somehow choose which object was being referred to. So it might get an instruction like this, brown horse, and then it would have to choose the object on the right here. And the trick we did was that we took the same agent architecture, but we posed this problem in two different ways. The first way was we just gave an image classifier this first image, and we asked it to say, is the correct object on the left or the right? So that's a simple binary classification problem. The second version is that we actually took an RL agent that saw the same first frame of the task, but then had to actually go to the object in 3D space. And the question we wanted to ask was, does the fact that the system is learning this task in this sort of embodied way where it's interacting with the environment change what it learns from a system that learns the same set of objects and colors, but in a static way from just images and pairings with instructions? And indeed, we found that it did. So when we tested the generalization capabilities of these systems, the agent generalized 100% of the time correctly, and the classifier generalized okay, but not that great. So this is just one illustration of the fact that embedding symbols in a rich enough environment can be essential to learning their meaning, at least from a small enough data set. Okay, So that's the end of the digression, back to symbols. So the fourth criterion we came up with was malleable. And the meaning of this, whoops, bad animation there. So the meaning of this is that because symbol meaning is conventional, it can be redefined in some cases. And this can happen both because, just in the way that humans communicate, at least, we tend to use meanings relatively flexibly. Like we can say a single word and we can mean many different things by it. We can say someone's name and we can denote many different things by the way we say it. Like if I'm like, Antonio, 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 I can say a lot of different things by saying the same name, right? And also, we think that it's useful often to redefine symbols because we've gotten something wrong. And so, the way we think about, for example, fundamental concepts in physics, for example, has required us sometimes to redefine what we thought of as an initially correct meaning. And so we think that it's important for systems to have this kind of epistemic humility where they're able to reconsider what something means in context if they need to. Now, in AI, well, it's definitely the case that language models exhibit some pragmatics. There may be some things that they're not very good at, which we'll come back to later on. And learning, of course, implies some sort of passive malleability in the sense that if you fine-tune a system with a new meaning enough, it will eventually change. But again, we felt that there was this sense in which humans can adapt meanings with purpose because we want to achieve some goal, because we see something that's insufficient about the existing meanings. And we haven't seen such clear evidence that language models do this in a purposive, self-driven way. The next criterion, very bad animation, sorry about that. So the next criterion we came up with was meaningful. So again, we thought that meaning was quite essential to symbol use. Symbol use is determined by conventionally agreed upon meanings. And we thought this was true even in more formal domains like mathematics. So math is often thought of as sort of the classic formal symbol manipulation domain. But we wanted to point out that at least some mathematicians feel that syntactic manipulations are only useful insofar as they're meaningful. And this is a great quote from Paul Cohen, who's a pretty brilliant mathematician, who said, "I was never able to successfully analyze proofs as a combinatorial game played with symbols on paper." This is responding to Newell and Simon's argument about what intelligence is. "To reason productively, one must essentially forget that the proof is going to be eventually transcribed in this formal format and instead think about it more intuitively." And similarly, Saunders McLean did something similar that you could sort of think of as being about how meaning is what solves the frame problem, which is strict formalism can't explain which of many formulas matter. That is what you should apply to solve a problem. The choice is determined by the ideas and the experience, the meaning behind the proof, right? And this is also kind of illustrated in the way that humans pursue mathematical understanding, right? Often when a theorem is proved, we don't just stop there, especially if it's sort of like some abstract proof that doesn't really give you an intuition for why the theorem should be true. We often want to find a deep proof that makes it clear why that theorem is true, that helps you to understand, because that helps us to build up a deeper understanding of the field as a whole. So what we wanted is models that similarly have a meaningful understanding of their reasoning process. And one of the negative examples we drew on here was actually this AlphaZero algorithm, which is a very good algorithm for playing Go. And the way it works is that you have some sort of learned meaning as a search heuristic, but there's this search algorithm itself that is built into the model that the model can't even directly experience, that it can't interact with, and that it can't understand or manipulate. And so we argued that because of this limitation, this system can't, for example, share knowledge intelligently across different branches of the search tree. And in that sense, it didn't have a meaningful understanding of how it was executing things, and that fundamentally limited its ability to be a truly flexible symbol manipulating system. Okay, so those were the 5 main behavioral criteria we talked about. And the last one, which I think is one of the most important, at least for how we think about symbols as in opposition to perhaps other approaches, is that we think of symbolic behavior as being graded. We think of symbol use as being not a binary capacity, but instead something that's more continuous, something that some system can partly have, but not completely have. And you may have already heard that in some of how I was talking about the examples before. So there's lots of examples of this in development, I think. So if you look at how children grow up, they're certainly receptive to meanings before they go out and construct their own ones, or Maybe that's arguable. Is Allison in the audience? No? Good. Okay, she won't tell me I'm wrong about this. And then they're also receptive to repeated meanings before they learn to reliably one-shot learn new meanings. And although we highlighted the importance of malleability, relatively few humans at any given point in time might be capable of finding a better meaning for any particular well-established symbol, like some concept in physics. So we think that symbol use itself will always be limited by cognitive, conceptual, or cultural factors. And therefore, like for humans, we expect that each of these abilities will also be graded and somewhat limited in our models. So we shouldn't be looking for perfect abilities as demonstrations of symbolic behavior. We should instead be asking more continuous questions like, how good is the system at exhibiting the kinds of behaviors we care about? So to sum that up, we see symbolic behavior as a constellation of graded capacities for engaging with and creating meaning. And just to put this in opposition to some of the approaches to symbols that are more classical, we don't think that symbolic behavior is equivalent to certain syntactic manipulations, which is often how it's seen in sort of classic GoFi approaches. And in particular, we highlight the fact that systems need to interpret the entities they're reasoning over as symbols in order to most flexibly make use of them. GoFi approaches can't, and as I'll maybe come back to in a little bit, most contemporary neurosymbolic models can't do that either. They're sort of like AlphaZero. They are using syntactic approaches like the tree search that AlphaZero uses, but they're using it in a way where the system is not able to flexibly reason over that or interpret it, and is therefore not able to most flexibly make use of it. And finally, we thought that symbolic behavior is not necessarily rule-based, which again is often advocated as an approach for more strictly symbolic systems. And just as a case study of this, to make it a little more grounded, because some of this has been pretty abstract, we thought about ethics in this paper. In particular, we find that a lot of these issues become quite salient when we think about ethics, because even philosophers still can't agree on a rule basis for ethics, right? And certainly not how you would impart that basis to a machine. And I think part of the reason for this is that human ethics is really fundamentally contextual and context-based, right? It depends on the situation. So if you think about a situation like a rule like don't hurt a human, there's many situations where we would actually think it's best to break this rule in order to sort of end up with a better outcome in the end, like re-breaking an arm to set it better. And rules, conversely, can often be too inflexible and therefore easy to circumvent. For example, a very famous, unfortunately famous example is if you have a rule or a law like don't discriminate on the basis of race, this might just result in the use of proxy variables like, oh, we're going to discriminate against people from this neighborhood. It's not technically on the basis of race, but it just so happens that this neighborhood happens to be mostly of one race. And so what we thought is that this is just an illustration of the fact that AI really needs to understand ethics as a holistic, meaningful framework rather than just sort of being given a set of rules that it has to follow. Okay, great. So that's how we thought about symbolic behavior in this paper. In the paper, we also tried to say a bit about where we think this symbolic behavior comes from in humans, and in particular, how they develop it. So one of the interesting things about human development is from a relatively early age, we show some evidence of quite adept social understanding, such as in this false belief task. From at least about 4 years old, I think, children understand that if someone puts something in one location, they leave the room, someone else moves it, and then the first person comes back. They understand that even though the child knows that the thing has moved locations, the person who left does not. And so they understand sort of like other people's perspectives and beliefs about the world and the differences from their own. So where does this come from? Well, we thought that we actually followed some ideas from Michael Tomasello here, who's written a lot about the development of human knowledge. And something that Tomasello talks a lot about is this early development of joint intentionality, which is sort of this fact that like humans tend to early on learn to attend to the same things or possibly innately attend to the same things as others. This has actually been argued, for example, to be one of the reasons that we are one of the few animals that have white eyes, so you can see where we're looking relatively easily, and it makes it easy for other humans to look at where we're looking and attend to the same things we are. And from a fairly early age, you get these interesting interactions between kids and their parents where they're sort of jointly attending to things, they're interacting with each other, and even before the kids can talk or even Babel, you start to see these almost language-like interactions develop where they even just like facial expressions going back and forth between the parents and the child develop very early. And Tomasello argues, and we sort of just copied this from him because we thought it was a cool idea, that these kind of things, these early development of joint intentionality leads to the development of conventional communication as a later ability. Okay, so what we thought based on this is that maybe it's really important to have systems that can interact while they're learning in a social way and take a shared or unique perspective and understand the difference between those two things in order to develop more human-like symbolic behaviors. Yeah, so basically in the paper, we suggested that for AI to develop the most flexible symbol using capabilities, it should develop those symbolic behaviors in the same way that humans do, which is by learning through social interactions and through culture. And in the paper, we talked about some early steps that we had seen in that direction that do some version of learning from recorded human social interactions. So one example of that, obviously, is language models like GPT-3, which, although it's not learning directly from interacting with humans, is learning from the sort of social interactions between humans that are recorded on the internet, which are a very, interesting sample of social interactions. Another example we highlighted is this imitating interactive intelligence work from DeepMind, in which agents were learning how to sort of like ground language in a simulated 3D environment based on imitating the interactions that two humans had in that environment. Okay, so we were excited about those works at the time. And then finally, we said, okay, well, we should try to put this in context with some other perspectives on symbols that have been given before. So first of all, we started by talking about behavior, but the other views on symbols are motivated by behavior as well, starting from Newell and Simon. But the kinds of behaviors that they tend to consider are different. And in particular, one that gets talked about a lot, at least in the neurosymbolic AI literature, is compositional generalization. And I think it's interesting in that context to ask how, so compositional generalization, just so we're all on the same page, is the ability to sort of like recombine elements compositionally in a language in order to sort of systematically generalize to the consequences. And the interesting question that raises is, well, how systematic are humans actually on these tasks? And the kind of funny thing is that if you look at the human cognitive experiments, you'll find that, maybe if humans are compositional like 80 or 90% of the time, people will say, look, humans are compositional reasoners. But then the people who are criticizing AI will say, oh, this transformer only got 98.4% accuracy on these compositional calculus problems. Therefore, it must be a failure of the model class to be really compositional. So again, we see this as just two examples of how systematic behavior may be one graded competency that's afforded by your environment, by the kinds of manipulations you've learned, your education, but that this isn't necessarily a necessary or sufficient demonstration of symbolic understanding, and in particular that mechanisms that guarantee systematic manipulation of symbols might not be the right direction for achieving what we consider to be symbolically fluent AI. And that's especially true if, like the MCTS and AlphaZero, they interfere with these aspects of more flexible symbol use that we think are quite important. So the next perspective, a lot of works have assumed that symbols must be discrete. And we think this is actually kind of misleading. I found the last talk very interesting in that regard. So the sounds that make up speech or the image of a Canadian flag aren't discrete, but they can be substrates for symbols, right? And even within a sort of classical approach, there's an important distinction between the entity being discrete and the entity serving as a discrete unit in a larger symbolic framework. And a very simple, intuitive way to think about this, if you've taken linear algebra, is the fact that a continuous vector can itself be a discrete element of a set of basis elements, right? Those two things are not incompatible. So we don't think that the definition of a symbol needs to place any sort of discreteness restriction on the substrate itself. And finally, the approaches that we really wrote this in response to were kind of new approaches to neurosymbolic learning. And these are things like probabilistic program induction involving neural networks and things like that. And we felt that despite their promises, a lot of these approaches might suffer from the same weaknesses of GoFi, at least in the implementations that were around back then. And this is one of the reasons that I think these approaches tend to be demonstrated still in mostly toy domains. But to the extent that these challenges are overcome, we still felt that these approaches would benefit from our perspective, focusing on the kinds of behaviors that we consider important and using social forces to encourage their emergence. All right, so I've told you a bit about our perspective. We took symbols to have meaning by convention, and this changes the focus on the kinds of behaviors that you would care about from a symbol using system. We suggested to achieve these behaviors, we should use interactive social development, and we thought that this would provide a fruitful path for AI research to achieve more human-like capabilities. Great. So now I'm going to try to say something about whales, which, again, I don't know that much about. So we'll see how this goes. And I'm actually going to start by not talking about whales, but rather talking about an important difference that we kind of elided in this work, but that I've been thinking about a lot in the years since, which is the difference between participating in interactions or observing and imitating. So for a child learning from social interactions with their parents, learning language, they're directly interacting, they're getting feedback on those interactions. Whereas GPT might be training on language interactions that are recorded on the internet, but it's just observing the way other people have interacted, and it's learning from observing and imitating that behavior. So when are these two settings different? Well, in AI, we actually know from a long history of research that there's some cases where interaction can be quite important for learning and for analyzing a system. And one example of this is if you're doing imitation learning in like a control task. Let's say you're learning to drive a car, you have some data set of humans driving cars, and the humans are driving down the road in various ways. Well, something that happens if you learn from just imitating this behavior, and then later on you deploy the system, it starts controlling the car, maybe it's going to go to a slightly different place than any of the humans have. And the problem is that depending how well the system generalizes, it might not know what to do in this part of the state space, and then it might just go off and start doing something crazy, right? So it's often important when you're training a system to get some active interaction in the training loop, even if you're mostly doing imitation learning, to avoid cases like this, where the system falls apart when you deploy it. And this also comes up in language learning, most saliently to me, because I've been learning Japanese recently, and Japanese, unlike the languages I'm most familiar with, has a distinction based on vowel length, which I at least at first had a hard time hearing. So for example, I might see this high school here and say something like, oh, Coco. And then my partner, who's actually fluent, would say something like, no, this is Coco. I don't know if I said that right. Apologies to anyone who's in the audience who actually speaks Japanese. But the point is that there's a kind of subtle distinction here that's fairly hard for me to hear and was very hard for me to pick up on until someone actually pointed it out to me. So interaction can be quite important if there are subtle aspects of the things that we're learning about that really matter, or if when we go off policy, it leads us to a weird situation. So interaction, yes, is important for actively correcting a system's mistakes, especially if they're mistakes that someone in the training data hasn't made before and been corrected on. And one interesting thing that comes up with this is that there might be some cases where there's interactions that become salient if you're a language user who's learning from interactions and you're trying to understand what people say. And one case that's been raised as a possible thing that language models aren't very good at learning, at least from base training, is the pragmatics of implicature. So the way this works is if someone asks you a question like, want to go to the bar tonight? And you respond, I have work in the morning, the other person you're talking to will interpret that answer as meaning no, right? It's sort of like, even though they're not explicitly saying no, there's some pragmatic assumption here that what they're trying to communicate by this is like, I have work in the morning, therefore I need to go to bed early, therefore I can't go out with you tonight. Whereas if you asked a different question and they gave the same response, like want to go to sleep early tonight, I have work in the morning, you would interpret the answer as meaning yes, right? So this is a kind of situation where based on your understanding of the world and your reasoning about the other partner's goals in the interaction, you kind of change your interpretation of what the basic meaning of this answer is, depending on the context of the question. And it turns out, at least according to this nice paper from Laura Roos a year or so ago, that this is something that pure language models don't learn that well, and they need certain kinds of tuning to learn to engage with this fully. Whereas if you think about the case when a child is learning from its parents' interactions, it would get immediate feedback if it misunderstood a pragmatic implicature, for example, and it would learn to understand the social meanings that are implied by the words. Okay, and more generally, we thought in this paper that symbolic behavior is learned through interaction and through developing contextual use of conventional behavior in context, right? It's learned through talking about meanings with people, defining new meanings with people, and considering the meaning of the symbols in context. And we don't, to be perfectly honest, fully know how much of that learning can be done from purely offline interaction and how much needs to be online in any particular generalization regime you want to make sense of. So the final point I want to highlight here is that interaction is also really important for assessment of a system, in part for the same reasons it's important for training, which is that, if the system is going to go off into some weird part of state space that it hasn't ever been in before, you're not going to discover that by studying how well the system makes predictions on the training data, right? You're only going to discover that when you actually test the system and you put it on the road and you're like, oh, now it's off on the edge of the road and it seems to be crashing. And similarly, if you take like these grounded agents that we're learning from interactions and you plot how well they do at sort of predicting the human data versus their actual interactive evaluation performance, what you can see is that although there's a correlation here, it's pretty weak and it's mostly driven by the fact that an agent that's really bad at predicting the human data is also really bad at interactive evaluation. Whereas there's a very weak correlation between how good an agent is at predicting the human data and how good it actually is when you interact with it. And what that means is that you really need to be doing this kind of evaluation in an interactive setting. People say similar things about language model evaluation, like benchmarks don't mean anything more than this model is probably generically quite good, but you really need to do some vibe-based eval, which means you interact with the system and you see how good it actually is. So what does this all mean for whales? Well, I probably didn't need to tell you any of this because you all already had this figure in your paper from a few years back. But basically, I think it's really important if you're trying to train a system to make sense of whale communication to actually do some interactive experiments. And in particular, you need to be able to interact with the systems that you're studying in order to understand whether you've learned something that's really generalizable and meaningful, or whether you're sort of like missing some key features of the system that you're trying to understand. Of course, an additional problem that comes up, unlike when I'm trying to learn a new language or something, is that you often won't understand the feedback you get back either. And that's why you guys are working on a much harder problem than I am. And I admire you for that. OK, so that's actually all I had to share. I'd love to have a broader discussion about these issues with you. Before we do that, I just want to thank my collaborators on this project, Adam Santoro, who was co-first author on it and really drove the initiation of the project, as well as Corey, Tim, and David. Thank you all for listening. And yeah, happy to take some questions.
Thank you very much. Any questions?
Maybe for posterity, are we recording these? I'm curious. You said this is how I was thinking about it then a lot, and I don't feel like I got a really good feel for how you're thinking about it now. So, do you want to tell us?
Yeah, that's an interesting question. I mean, to some extent, I feel like a lot of the arguments we made in this paper still hold up. On the other hand, like, I guess what I would say overall is I'm not sure that this paper moved the AI field forward, in the sense that I don't think we or anyone else really knew what to take from this paper about what to do next. So maybe the sense in which I feel like I'd think about it differently now is that it seemed like we learned more about AI from trying things and seeing what worked than we did from trying to think about the meaning of symbols. Now, I'm not ruling out the possibility that some of these ideas won't be useful in the future, and I still hope they will be. But that's sort of, I guess, my feeling has been that I learned more from the more empirical projects I did, like the one on sort of embodied learning of language, or the other ones we've done more recently on sort of like learning about causality and things, studying how empirically what systems learn from data, than I did from trying to think about the definition of symbols.
Talk. I am very confused by many things. I have many questions.
Good, me too.
Let's start with two. First one seems, okay, what is your opinion regarding this statement? What you showed here seems to imply that you cannot have a language, a symbolic system of a certain complexity appear out of nothing. You can only evolve it from simpler systems exactly because of this requirement of interaction. So how do you interact if you don't have any symbolic system and so on? And how does that, what do you think this says about, the social complexity, what's the hypothesis about the social complexity, origin of language and so on? And then the second part that I really like the scheme and the thing, the thinking behind this that sort of has me confused is, it feels like there are many moving parts. We are sort of putting together symbols for communication and symbols for thinking, so do we need those for that? And I know this is, a general problem, but for example, if you talk to psychologists, there is the whole point about symbolic bindings. They don't really care about what the symbols are and how that, for example, limits our capacity to do multiple things at the same time. Do you have thoughts?
Yeah, great question. So on the first point, which has now slipped my mind.
Symbolic complexity growth.
Yes, okay. So we don't think that this is a necessary criterion for symbol use, but we think it's, we take inspiration from the fact that it seems to be important to the human development of symbol use. That's what I'd say about that. So we think that it's probably a useful curriculum, but we're not saying this is the only way that symbol use can happen. But that said, it does seem like it's pretty, it seems like there's at least a fairly strong correlation between sort of like more social animals and more language-like communication systems, more symbol-y things like naming, arbitrary naming and things. So, we take that as weak evidence because, of course, there's a lot of confounding factors in common that this is an important, at least the easiest path to developing symbol use. So for the second point, I guess, there is a lot of debate about this, including to some extent among these different authors of the paper. But to give you my take, which I think Adam at least would agree with, I think that human, the sort of like the extent to which we use language for thinking is a cultural product mainly, and it's sort of a consequence of our learning language use from a relatively early age, and possibly in particular it's driven even more by formal education. And that, there's interesting evidence on all sides of the debate about this, but that's my take on it. And the other thing I'll say about that is that's very different from saying that language is necessary for our thinking. And in particular, I think those things kind of tend to be anti-correlated. So I'm someone who thinks that language is definitely not necessary for our thinking, and that our thinking doesn't occur in the language-like parts of the brain, which I think has been backed up increasingly well by the evidence in recent years. That's my take, but several of these people would probably disagree with me on that. So, don't blame them for it.
Shane first.
Go ahead.
Thanks. Yeah, I was curious what you think about recent attempts to locate concepts as vector embeddings, and if that relates at all to symbols as you're describing them, or if that could be a starting point for getting to something to do with symbols.
Yeah, that's a great question. So I guess I find the work very cool. I tend to be a little skeptical, or like, I think it's very hard to say that you're capturing like the full sense of a concept in a single vector, not to sound like a classical linguist, but like, I think that, if you look in a model and you find, let's say like in a language model, you find some vector that's, or, loosely speaking, a vector that's associated with like the Golden Gate Bridge, right? Some sort of pattern in some higher dimensional embedding space. And then you can sort of intervene on that, and you can make the model be more Golden Gate Bridgey, as we've seen recently, which is a very, very cool example. That tells you something about how things are being represented in that model, certainly. And it tells you that there is something like Golden Gate Bridgey about that concept. But it definitely doesn't tell you that that is the only way that Golden Gate Bridge related things are represented in that model. And I guess that's sort of the key missing piece for me. There's no like necessity condition on that that pattern being the only way that that concept is used. So I guess like I think it's a very interesting way of pulling out like hypotheses about what might be going on and like possible concepts, but it isn't necessarily sufficient. And then the other thing I'll say about that is from some older work looking particularly at these kinds of things, and some of our work looking in a slightly more abstract way, we actually think that there's a lot of cases where these concepts that you pull out are very data distribution dependent. Kind of similar things happen in neuroscience with like grandmother cells, right? It's like, oh, like this cell only responds to grandmothers. But, you know, there's sort of been arguments since that, well, like maybe in a like different context, it would actually be responsive to other kinds of stimuli, or like, you know, something that looks like a place cell in the hippocampus, but like actually it's kind of sensitive to other signals too. And similarly, so there was a very nice paper showing this in one of the earlier language models, BERT, that there's this one neuron that on this training data set looks like it's like a song name identifying neuron. Like the only thing it responds to is song names. And then it turns out that on a different data set, it's like, it does something completely different. Like it responds to like, you know, like math concepts or something. So like you can have these cases where like the under distribution shift, your interpretation of what a unit in a model is doing completely changes. And that's actually maybe like quite fundamental to how these models work, right? It's like the reason that you get sort of interesting generalization from deep models is because there's sort of non-trivial sharing of knowledge across different concepts that we don't really know how to explain or make sense of in most cases. There is some theory that can make sense of it in certain cases. And I think because of that, it's very hard to look at any particular interpretation and say something too strong about like what is being represented there. Yeah, and then last point I'll make about that, just because I've been quite interested in some of these concepts recently. So we just put out this paper on sort of like the representations that systems learn and what gets represented in them. And the point of the paper is that the representations are actually quite biased in what kinds of things they tend to capture. And so, for example, if you train a system on something like that's complex and nonlinear and something that's simple and linear, you'll find that most of the variance in the representations is carried by the simple linear task and not the nonlinear task. And what that means is that if you're doing analyses that are like, oh, let's pick out the things that explain a lot of variance in these representations, let's call them concepts, you're going to be biased probably towards considering like the simplest things that the model is doing, which might not be at all the only important things that it's computationally doing. And I think that's a very fundamental problem for neuroscience perhaps too, but definitely for machine learning interpretability.
Bring up the slide where you have your 6 different definitions. Sure.
So I think it's really interesting, Ryan's question about how you think about this now rather than before, because I feel like in animal communication, we spend a lot of time doing the sort of theory problems and agreeing on sort of coming to consensus about the definition of these different parts. And so this is really interesting from my perspective. I'm a whale biologist. So do you think if you can show these 6 things without having any interaction in terms of trying to answer semantic meaning of specific sounds, do you think you show these 6 things in some way that it's inherently a symbolic system without necessarily being able to ascribe meaning to any of the symbols?
I mean, I think it would be very hard to show these 6 things without being able to ascribe meaning, right? And particularly like the meaningful one is a bit tricky. But I do like, you know, and then the other thing I'll say is like we have this graded thing in here because we think it shouldn't really be thought of as a binary, right? We think that like many systems are like symbol users to some extent, but maybe not in as rich and flexible a way as humans are. So I definitely think it would be like, you know, if you showed that systems captured some aspects of all these criteria, I think that would be a great starting point for like thinking about what kind of a symbol user a system is. And probably it's sufficient for saying the system uses symbols in some sense. But then the graded piece comes in and maybe like isolates me from making any too strong claims from from that kind of evidence. But yeah, I mean, I think, you know, the thing we were trying to do here was to set out some criteria that could be more practically useful, and that you could go out and like look at a system like a language model or a language RL agent, or even, something that doesn't use language at all, just like a video model or something, and say like, well, is it receptive to new meanings? Can it construct a new meaning? Can it like change the meaning of something in context? And like those kind of things are like, relatively like, possible to assess with a wide range of systems. So I hope it's a useful set of criteria, and I'd be interested to chat more later maybe about.
Yeah, absolutely. Thanks.
Extent.
Cool talk.
Thanks.
Thanks for the exceptional talk. I think this paper still gives very good concepts to reason also about recent results. Especially, I think it's very interesting what you said about GPT, like the fact that it seems that we need some social interaction, and then indeed GPT is trained on a lot of text describing social interactions. My question is on this, like, if this is the case, it's interesting that this social interaction is essentially unstructured, like it's just plain text. It's not that GPT is architecture is like distinguishing, for example, what one person say to what another person say. In our context in SETI, I think this can be interesting because may say to us something about how much can be important, for example, to disambiguate which whales are saying what, but just taking all the raw sounds can be enough. So if there's something to comment about the fact that this interaction can be completely unstructured, or you feel that maybe if it is structured could help.
Yeah, very interesting question. So I think, the dumb but obvious point to make here is that GPT-3 or 4 learns from a lot more data than you're going to have for whales. And so it does at some point pull out these sort of like clusters, and you can see that it's sort of representing different entities differently within the data. At least you can see this with some language models. And, people have written sort of like theory pieces, including my colleague Murray Shanahan, who wrote this nice paper on like role play in language models, which is essentially this story that they're sort of like, they're learning that there's different clusters corresponding to different like roles within the data, and they can even sort of like within the context of a conversation or across conversations, they can sort of like adopt different roles in response to the context. So I definitely think that like, given enough data, a system will learn that. It's not clear to me that that's the answer might be different at the scale of data that you have for whale speech, but I'm not sure. It might be sufficient. The other thing I think I'll say is that like, it's interesting to think in human learning and also presumably in dolphin learning about the extent to which our experience of language, how much of it is driven from these kind of interactions and how much is driven from other people using language in our vicinity that isn't directly interacting with us, right? So I saw a talk from Mike Frank recently, who does sort of like child language development. And one of the things I found was interesting was that like in their corpus of child speech, like speech that's heard in the vicinity of children, so they're recording video and language from the child's perspective, I think more than half of the speech was actually not directed to the child. It was like the parents talking, or it was like the TV was on in the background or something. And so, maybe children also are learning quite a lot of their language from interactions that they're not directly participating in. So that's probably an important source of learning for them too, at least in certain kinds of contexts. And I think it would be very, very interesting, although I don't know of any work on that per se, to study like what role exactly that plays and how well children are able to make inferences about those kinds of things.
It's a very nice talk. So my question is, what are some examples of strictly not symbolic systems? And how do we know that non-symbolic systems are incapable of exhibiting similar kinds of behaviors?
Yeah, that's a great question. I mean, so these definitions, because of the graded hedge at the bottom, are kind of like quite flexible. But if you think, so one of the examples that I really liked from this Turetsky and Pomerleau paper that I mentioned earlier was they talked about a doorbell as being a symbol system if you think that any pattern that designates is a symbol. And I think from our perspective, the doorbell's not really receptive. It can't learn anything, and it doesn't really meet any of the other criteria. So from our perspective, we'd probably say at least a doorbell is not a symbol using system. But beyond that, it gets kind of hard, right? Like even a computer as such is like, at least receptive in some sense to some things. And so like, I think we're kind of maybe too okay from some perspective at saying that many systems exhibit some sort of like very slight use of symbols. But I think when it comes to like, these sort of like constructive, for example, I think is a good criterion that cuts across a lot of systems, including current AI systems. It says, well, like if you can't construct new meaning in a purposive way, if you can't assign a new symbol in a purposive way, then you're not exhibiting a lot of the important symbol using abilities that humans have. And this is a criterion that is much more selective, and relatively fewer systems would correspond to this.
So a couple of times you distinguished icons from symbols, which I think makes sense because we have these arbitrary symbols and then these icons that are motivated to some extent, again, graded, but motivated. But I mean, it's also the case that there are a lot of iconic or motivated symbols in human language, for instance, and also like there's a lot of behavior results that people are sensitive to the iconicity, and it affects things like learning and memory and even language development. So I would be curious, like, where do you see that it fits in? Do you see iconicity and sensitivity to iconicity as something separate, but that interacts with symbolic behavior, or is it also a part of symbolic behavior?
Yeah, that's a great question. So I think I briefly mentioned that we originally had 7 criteria, and the one that we got rid of was separable, which is the ability to separate the meaning from its substrate. We got rid of it for 2 reasons. One was that we kind of decided that was sort of overlapping with embedded to some extent, and therefore maybe it could just be combined with that. But the other one was that actually kind of motivated by thinking about some of these cases where there's sort of like this smooth gradient from like iconic representations to symbolic ones. Like you can see this in sort of like development of certain writing systems, for example. And there's also this, some interesting experiment which you may or may not have been referring to, but on sort of like non-arbitrariness in the way people use words to refer to meanings, like this sort of like Kiki versus whatever experiment thing. Yes. And so like, I think that's very interesting, and it probably gives insight into like the way that humans pick up on these sort of reference games to begin with. At least that would be my very much guessing hypothesis, because you certainly see that in child development, the things that the first words that they acquire are things that aren't super abstract, but they're things that are like very grounded and salient to them, and maybe having some like sort of semi-iconic like onomatopoeias, or like things that are not totally arbitrary bindings of symbol and referent, help them to pick up on this sort of like more abstract pattern of using arbitrary symbols. So I do think it could be important. It could also just be sort of a natural consequence of the fact that there, like, if there is some non-arbitrariness, then you'll probably use iconic things where you can get away with it, and could just be that too. But yeah, very interesting question.
Yeah, I have a question. What is the relationship between your definition of symbols and the notion of narrative structure? Namely, we look at the world, and what our brain is constantly doing is trying to find an explanation of it, have an ongoing narration for what's happening. Are the symbols what the narrative structure is made of?
Yeah, good question. So I think like, I do think symbols can be and probably for most people are, an important part of that narrative structure. And I think part of what we were trying to get at with the embedded criterion is the notion that the symbols should be about things in the world and will sort of emerge from our experience of things in the world and trying to make sense of that experience. Maybe that kind of maps onto the constructive and meaningful criteria too. But I don't think, as I mentioned earlier, I don't think, for example, that language is the only means by which humans can think. And I don't think that symbols are the only means by which humans can think either. Certainly we can think in icons and indices, but more fundamentally, I think that not all of our thinking even necessarily maps onto nice discrete categories like these either. So I tend to imagine that there's some sort of, more continuous, more dynamical systems like process that is driving our thinking, and which maybe as an emergent consequence produces some things that look kind of like symbols or icons or indices that we perceive and maybe communicate to others about as more discrete entities, but that's being driven by some underlying more continuous computation. That's how I think about how intelligence works and how we think about making sense of the world. But that's very much a hypothesis, and it's a hypothesis that many people would disagree with. So,
well, recent data also shows that different people think in profoundly different ways. Some people are fantastic, some people are not okay, some people think verbally okay, and it's something you never know just by interacting with them without actually asking what is your experience of thought.
Yeah, I mean, I think that's a very interesting example. So part of the way I think about this, and I've maybe kind of alluded to this in other cases, is that I think of language as a thinking system as being very culturally defined and also sort of imparted to us in part through education. And I think that part of the reason that we wouldn't see, it's not so easy to see from talking to other people unless you ask them very directly about their internal experience, that they would think so differently from us, I think is because we sort of learn in a culture that sort of more homogeneously defines how we communicate and sets up concepts that are sort of more commonly abstracted and shared across people. And so I think it's maybe almost by design that that's true, that even though we might think in slightly different ways internally, in the ways we communicate externally, it sort of abstracts away from those patterns of thought. But it can be quite important in differences in creativity and coming up with different kinds of ideas might be better afforded by certain underlying computation systems rather than others. Maybe some people are better at solving certain kinds of problems and others are better at solving other kinds of problems. And I think those things will manifest behaviorally in certain ways, but maybe will be sort of abstracted away by the language we use to communicate more often.
So I think we're out of time. I suggest we continue it offline. Andrew, thank you very much, and for everyone for asking questions. We now have half an hour break, and then we reconvene at 12.